Thank you, Tim. Thanks for having me. It's cool to be here. All right. Yeah, as Tim said, so I want to talk about models in the programmatic advertising space, specifically about traffic shaping. Brief introduction about myself. Tim already introduced me, so just wanted to point out a little bit about Simplaex. So Simplaex, I've been working at River for Simplaex. So River is the product, Simplaex is the company. For about 2 years now. Simplaex used to be called Game Genetics when the focus was still on in-app targeting. It's about a startup of 30 people. More than half are in R&D actually. And what we sort of lack in size, we make up in diversity, I wanted to say. So we have 60 nationalities and not one, but 2 office dogs. So every species is represented. Yeah, so the first release of the product was in early 2019, River. And yeah, so what I'm going to talk about is basically the product of the machine learning team. There are currently 4 people and yeah, working on River. Okay, very brief outline of the talk. I will start with a few words on programmatic advertising and real-time bidding, just to set the context right. Then I will introduce the traffic shaping problem, which in a nutshell is just how to select fewer auction participants without risking too much revenue in the auctions on a high level. It could be just said like this. And then I will describe how we actually approach this problem. We basically split it into 2 parts. And the first problem is what I would say is the more purely machine learning kind of problem. So it's a predictive problem where we try to model and estimate the value of an auction for each of the participants. And once we have done that, basically we can use these predictions and feed them into the second subproblem, which is actually the actual minimization of the number of participants that we need while still like not risking too much of the revenue. This is a more purely like optimization kind of problem. So if you think of operations research, there is yeah, so mathematical optimization basically. So it's sort of machine learning. That's the nice thing. What I like about it, that there's both my kind of main interests, machine learning and optimization, are part of this problem. Finally, I will talk a little bit about some operational challenges we had to solve when actually deploying those models. Okay, so in a nutshell, what is programmatic advertising and real-time bidding? So as you all know, there is no free content, right? So whenever you browse a news website in the web or you use a supposedly free app from the App Store, the money has to come from somewhere. So you're basically part of what is called as supply or inventory of potential ad impressions. So you're basically generating, by browsing pages, generating page views. These page views will then be monetized. And the way this works is that the website or the app is connected to a so-called supply-side platform, or SSP in short, that whose only job is basically to monetize these impressions. And the supply-side platform is either connected to an ad exchange or it's actually running the ad exchange where the auctions are taking place. And you need, of course, for an auction, you need bidders, right? So you need participants that are willing to pay money for those impressions, and they are represented by the demand-side platform, or short DSPs. These DSPs are acting as agents for the advertisers that actually have products to sell and to advertise, basically. So yeah, within the scope of this talk, I will use the terms demand-side platform, DSP, bidder, auction participants. I will use them interchangeably, so it all means the same thing. So programmatic advertising is full of confusing terms, so I don't want to take away from that. Right, so but first, what is real-time bidding? So in programmatic advertising. So first of all, auctions, they need to have a very low latency. So if you think about it, you come to the page, the page gets loaded. I mean, at that time, already the auction needs to be running basically from end to end. Bids need to be collected. Things are kind of running behind the scenes. So there's a very low latency requirement. Also, typically mid-sized supply-side platforms have billions of auctions per hour. And this is a very, very high number. And it can be partially explained that auctions are actually kind of duplicated, like to many places, just for performance reasons. But then also I mean, oftentimes you have bots involved and so on. So there's a huge amount of sort of duplication and so-called waste, maybe. And only 5% of the actual requests to participate in an auction are answered. So 95% just kind of disappear. Also, the typical revenue per request is fairly low. So it's in the order of a few cents, 1-2 cents per 1,000 auctions. But maybe you're wondering, like, where's the optimization going in? So it turns out that the supply side platform actually has to pay for outgoing traffic. So, for example, Amazon charges you for making requests to like other places. So usually there's a different pricing for destinations that are closer compared to like further away. But so these outgoing auction requests, bid requests, they actually cost a lot of money. So the original goal of our product was to reduce these costs for the SSPs by just reducing the number of requests that are sent out, basically by running these auctions more effectively. And since recently, we also extended the problem a little bit. So by introducing limits into how many requests are sent to a single bidder. But I'll talk more about this at the end. Okay, so where's the optimization, where's the machine learning problem here? So if you think about it, so you're an SSP now, you want to run an ad auction. So every ad auction has an intrinsic value to all these candidate participating bidders. So for example here, so the SSP is running this auction, sends requests to these 4 bidders here. To move the Zoom window. Right, and so the top one and the bottom one, they reply, the other ones don't even reply, and they reply with 2 different bid prices. Now, if the SSP somehow magically knew ahead of time which bidder would participate in the auction and how much they would bid, then you could somehow reduce this amount of requests while not sacrificing much of the revenue. And so this specific problem is part of the problem, or part of the theme of problems that are called traffic shaping in the industry. Yes. So, but how do we formulate this as an optimization problem? So let's say, let's for the moment assume you would know exactly in advance what are the auctions that are going to happen in the next hour. So you know exactly what impressions will there be, you know what the responses of the bidders will be, how much revenue they will bring. And your goal is now to maximize the amount of saved requests or minimize the number of requests sent while losing at most a fixed fraction of the total revenue. So then the simple optimal solution is basically just to sort these requests in increasing order of revenue. So you start with the request that yields the least amount, say 0, because they never get answered. And you keep on eliminating these requests. You save those requests, you decide not to send them. So you basically start at the bottom right of this curve. On the x-axis here is the fraction of revenue retained. And you kind of progressively move more to the left and to the up, because you keep on saving requests, you decided not to send them, so your fraction of requests saved sort of increases. So you're moving along this curve, right? And that's what I would now call the optimal curve. However, in practice, we cannot really use that because we have no knowledge of these future requests arriving, right? They come in an online fashion. You don't know the future. So we need to estimate the revenue per request. And the way we can estimate them is by segmenting essentially your traffic. So segmenting all the possible ad auctions or ad auction requests into these different groups based on common properties, common similarities, basically, right? But on a high level, let's look at the high level first. So on the high level, you're starting with a set of ad auctions with requests per bidder. And we decide to take a share of these auctions apart. So we do not optimize them. We keep them as a control group. And then we are able to use these control groups, auctions and requests to train a model, like a regression model for revenue per request, which I call now here the predictive model. And then, as said earlier, so we can use the outputs of this model to optimize thresholds on these predictions. And so more about the details later, but the goal is for every auction to have a list of bidders or a recommendation of bidders to which the request should be sent. So let's start with the first subproblem. So on a high level, if you look on the right here, so auctions could be seen as basically tuples of values here. So you have some value for operating system, OS, device type, country, and so on. Or OS could be Windows or iOS and so on. And as said, so we keep 10% of the auctions apart and use them for training. So what do we do with these auctions? We aggregate them according to into these traffic segments. So let's say we have a very simple way of segmenting the traffic. We only look at operating system and device type, and then we count the number of requests in the so basically if you want the number of requests that would be sent if we do not filter anything, and we account the revenue these requests will make. Okay, so we actually so we tried with different ways of predicting revenue per request, so different kinds of regression models, from regression trees to XGBoost, and some also simple versions of neural networks and time series models. And we also experimented quite heavily, I would say, with feature encoding. So most of our features are categorical, and so you would think that feature encoding is important here. But so far, it really seems that regression trees work best for us, and some fairly simple feature encoding. And so we sometimes can improve our KPIs by switching to a more complex model, but basically the added complexity does not, at the moment, warrant like a more complex model. But yeah, we do use different features for different customers, and of course we are fully GDPR compliant. So yeah. So let's look at the second problem. So now that you have these revenue per request values coming from the predictive model, or these predictions, we can use these to determine thresholds. So let's look at this example here. So here's like a table similar to the previous one, where we have operating system and country. But now we also have on the right column here, we have the prediction. So the prediction for the revenue per request for this traffic segment that is defined by OS being Windows and country being US or USA. Yeah, so there we basically just count the number of requests and the amount of revenue. And if you look at the first column, you only have one value for prediction. But if we look at, for example, the red rows here, so this is for iOS and USA, we basically determined that within a range of values, like from 0 to 0.004 of prediction, we see about 5,200 requests and about $42 of revenue. This is basically a cumulative aggregation here. For iOS and USA, in a range of prediction values from 0 to 0.0082, we see a couple of more thousand of requests and exactly the same amount of revenue. So if you would need to choose for this segment, iOS and USA, you would need to choose between a threshold of 0.004 and 0.008 or 82. There's basically no reason to use the lower one, because the lower one will, the higher one will save more requests and potentially risk like the same amount of revenue. So this is something that the optimization will pick up. So here in this sort of red rows, it was easy to see, but let's say if we look at the blue rows here, so the blue rows here, we also have two predictions coming from the regression model for Android and Switzerland. So here's like 9,500 requests, and here we find about $25 of revenue. And for the higher threshold or potential threshold, we see more requests, but also more revenue that is below that. We find below that prediction value. So below that would be lost if we used the prediction as a threshold. And if you think about it, what the optimization should do would be basically, for example, in this case of these two rows here, you can think of this as items. You can think of it as choices of items. So Android, Switzerland, and the threshold 0.29 that both have a weight, which means this would be the amount of revenue you would lose if you used 0.0029 as a threshold for this combination, but also like a value. So this corresponds to the number of requests you save. And similar for the other row. And if you are familiar with the kind of classical computer science optimization, like considered hard optimization problems, you will recognize this as a version of the so-called Knapsack problem, where we try to basically pack items. In this case, these are traffic segments in combination with thresholds into a container that has a fixed capacity. So here our capacity is the amount of revenue we are willing to lose, basically, or we're willing to risk. We don't know if we're going to lose it all, but in the kind of threshold optimization part, we consider it at risk. Okay, and it's not the plain vanilla Knapsack problem where you just try to pack items into a container, because also we cannot basically use these two items at the same time, because we have to decide we can only use one threshold. And I believe Wikipedia told me that this is a version that is called multiple choice Knapsack. But yeah, I only read it there. Okay, so the goal here is to set these thresholds such that we achieve a required level of revenue retention. So let's say we are willing to lose like 1% of revenue in the worst case, while maximizing the amount of requests saved. Okay, so how do you think, like, how we approach this problem is our algorithm is actually an extension of the kind of more classical dynamic programming algorithm for Knapsack that we modified quite heavily, basically, to make it suit our needs. So there is clear scalability issues. If you, depending on how granular your traffic segments are, you fairly quickly get into like runtime problems. There's memory is an issue and so on. So we did some optimizations there. But also we were able to extend this sort of plain case of minimizing the number of requests sent subject to like a revenue retention to also other interesting cases. For example, one of our customers approached us and said, it would be really nice if we also could use limits on the bidders. So you have these DSPs that are participating in the auctions, and they themselves, of course, have a computing infrastructure. They can only handle a certain load. So they what is then defined is its so-called query per second limit, a QPS limit, that must not be exceeded. So it must not receive more than a specified amount of requests. And we are able to add that to the optimization as well. And the other type of extension we did was that to use upper bounds on the per bidder revenue loss. For example, for the SSP, it may be considered a bad business decision to completely cut out bidders, because there will be basically their revenue would be lost completely, and that's not nice. So we also added these kind of constraints there. Quick words about the operational challenges. So I mean, the model works best if bidder behavior is more or less stable, at least over a 24-hour period. But we also did some extensions to like more hourly granularity. And also for the threshold optimization with QPS limits, it's very important to get the data, basically get fresh data in a continuous fashion. But most issues we were able to solve by just having better monitoring of the model quality as well as the data integrity. And one thing to point out is that basically the computing environment of these SSPs is very diverse. So our library needs to support different kind of languages for serving the model recommendations. Quick, I'm seeing I'm running out of time. So just a few words on the results. So we were quite happy with the solution as it is right now. So like regularly we see some performance in terms of requests saved, about 40 to 70%, depending on the SSP, of course. The traffic quality varies a lot per SSP. So if it's basically easier to save requests, we'll perform better, and sometimes it's more closer to this 40%. But we are also losing very little revenue, so it's typically in the order of 0.5%. And so this QPS limit feature was received very happily by the customers. Also because if you compare ourselves to like just a random sampling method, we also are able to measure a quite nice uplift in the terms of 30%. So more extensions are planned here, and so it's an exciting kind of line of work. And now I'm ready to receive questions if there is any, and like to thank you also for listening to me, and once more Tim and his colleagues for having me in the conference.
Yeah, thanks, André, for the interesting introduction to programmatic advertisement, introduction to your advanced models. So like one question that naturally arises, I mean, nowadays contextual targeting is like becoming more and more important, but I never heard something like the word content in your talk. So are you completely agnostic of that? Or?
We experimented with some kind of labels that you get for free about the content, but it's really true in the case. So we don't look at the natural. I mean, if you think of the NLP part, right? When you like web pages, there's a lot of like NLP data. So we use very little of that. And so just basic things really. And this is just because of the sheer scale of the problem, right? I mean, if you have like millions of, web pages, basically, you're not, I mean, just if you just would try to crawl them all the time and derive like textual features from those, it would be very costly, basically. And especially if they're changing over time. But it is one of these directions I also personally would like to go with more. And as said, so we did a little bit of exploration with neural nets, but we just scratched the surface there, really.
We have a question from Didier Orel, and he asks, could you please repeat how you got the measurement of the revenue loss of 0.5%? So.
Yeah, so we basically extrapolate by the performance inside the control group. So we continuously let the model run also on the control group. And there we basically have what we would consider ground truth. So assuming exactly the same auction would be repeated in this same hour, then we could apply the model, and it would basically, we have a term like winner recall is a metric. So we would recommend the winner, the winning bid. And therefore we know that we would not lose that revenue that would derive from this request, basically. So yeah, we have a more like a simulation, continuous ongoing evaluation of the model on top of this control group.
Okay. You mean it seems to be like a free lunch? Like, is anybody losing in this game? Maybe the network providers, Amazon, but even like the DSPs, they should be happy that they don't get so many requests, or are they kind of reacting in some way to this? And is there like a balance of powers going on? So.
Exactly. We think they should be happy. I mean, what we sometimes get are these things that, oh, look, we started the filtering and this DSP started to get like far less traffic. Is there something going on? And then usually we are able to show that, okay, this is because of, compared to other DSPs, its revenue per request has gone down recently or so. So we are able to find these likely explanations for this. But yeah, exactly. So in terms of this QPS limits, for example, we have recently started to basically make this kind of analysis where we say, okay, look, the QPS limit is 5,000. We would be able to, serve more, get more revenue if we just doubled it or so. Maybe you guys, we're talking to the SSP directly, that's our direct customer. Maybe you should, talk to the DSP. Maybe we should increase that limit.
Okay. So maybe they complain that you're giving them bad predictions. So they say, okay, you make the bad prediction on us. So please increase. And like, how does it like an implementation of your solution work? Are you kind of like a man in the middle for DMP, or how does it? How do you get integrated? Because you don't have your own ad server infrastructure, something.
Right.
Like that.
Right. So the model is actually packaged into this, like via this sort of library adaptive thing.
Okay.
And that is running on the same nodes as the SSP. So inside the SSP data center, they regularly fetch updates to the model. And because of this low latency requirement, so we couldn't like run our own servers. That would add basically too much latency there. And it also would be very costly because before filtering, you would need to, ask our server, should I filter or not? And this a bit defeats the purpose then. So yeah, we are very close to the SSP. Yeah.